When you go through a reaction, you are combining or at least rearranging atoms, which atoms are attached to which other atoms, and that of course causes some change, and that's a chemical change. But another thing that happens sometimes is when you mix various chemicals together, it just makes a mixture. They haven't chemically combined, you just kind of blended them together. So I just want to go through a little bit about mixtures and compounds and how you would separate the two and how you would classify these things. Just in general, recognize the law of conservation of matter. Matter is neither created nor destroyed. As you go through a chemical reaction, if it's a chemical reaction, you are rearranging atoms. They are all still there at the end. You're just changing which atoms are attached to which other atoms. That's really all that's going on. Now, if you're going to classify matter, you can classify it in a couple of ways, and I just want you to recognize the options here. One is, of course, pure substances. Pure substances could be an element, or we'll mention a compound in a moment, but they have a unique set of physical and chemical properties that is consistent throughout. It doesn't change, and you can't really separate these things out from one another very easily anyway. Well, you can, but we'll talk about some of the detail here as we move along. But again, unique set of properties. Elements made of a single type of atom, the smallest part of an element is the atom. You cannot separate those into simpler substances. If you break apart an atom, of course you have protons, neutrons, and electrons, and that's common to all atoms. So that's the smallest, an atom is the smallest representation of a particular element. They all have symbols, and we'll learn some of these as we move along. Most of them have two letters, some of them have one. You will see on periodic tables occasionally three letters, like UUU or something like that, like unilunium or something, and that's basically a Latin term for the number of that element. When they first discover it, they have to put something on the table, so they give it kind of just a three letter symbol until they kind of come up with a name, and then they give it a more proper thing. But all the proper symbols have one or two letters. And some of the more unusual ones, like K for potassium or Na for sodium, Au for gold, you'll see those on the screen. A lot of those unusual ones, people are like, why is Fe iron? And it's from its Latin name ferrum, or mercury was hydrogyrum, or lead was plumum, and those are from kind of the Latin names for those elements. They've just been known about a while, and so that's why some of those element symbols seem rather odd. Why is sodium Na? And that's why, from the Latin natrium. If you look at the periodic table, of course, you will see some common things. I just want to point out a few of the things that you'll notice when you look there. Of course, you have the atomic number, which we'll talk more about in other chapters, the number of protons, the symbol, the name, and the atomic mass. And again, we'll talk more about that in some later chapters as well. Now, when you combine these atoms, when they chemically bond, when the electrons are either transferred or being shared, you get a bond. Ionic or covalent is what I just described. Again, we'll talk more about that later, but it is made, you've got more than one type of atom chemically combined in fixed proportions. For instance, H2O, water, is always 2 hydrogens for every 1 oxygen. So there's a specific ratio, and that is represented by a formula. And again, you'll see some formulas on the screen. Please notice every time when you're writing formulas, if it's a new symbol, you must do a capital letter. The small number to the lower right, the 2, that is a subscript. It refers to only what is immediately in front of it. So in this case, I'm saying that I've got 2 oxygens per that 1 carbon. Now, those were chemical combinations. I've made compounds there is what that's called. I could also mix things, and you generally have 2 different ways you can mix things. You can mix them either heterogeneously or homogeneously. Heterogeneous, different form, you can see the different parts. Salad dressing, you have oil and water and they separate. Chocolate chip cookies, you can see the cookie and the chocolate chip. Sand and water, so you can see the different parts. That's heterogeneous. Homogeneous, it is the same throughout. The items have not chemically combined, but they have blended together in a very uniform way. So it may be clear, it will not separate on standing, but it is truly a mixture. And again, I'm going to go through some examples of that in a moment. One very common one for a solid mixture, a solution, is an alloy. When you blend metals together, you get them in the molten state, you blend them, and as they harden, you can alter their properties. Brass is an alloy where they've mixed copper and zinc. Steel is an alloy of carbon and iron. Bronze is an alloy of copper and tin. And again, why would they do this? Because it improves the properties. Stainless steel is chromium and iron, and of course that prevents it doesn't rust like normal iron does. Alloy brass is stronger and has harder. It's a harder element than the copper and the zinc individually. So you get some unique properties, and it allows you to use it for different applications. To give you an example of what this might look like, another example would be gold. 24 karat gold is 100% gold. If you'll notice on the left there, pure gold atoms. But they blend in sometimes other metals. Why? Makes it a little bit harder. Pure gold is rather soft. It also can make it a little less expensive. Things like copper and silver are a little bit cheaper than gold, and so there's some other benefits to that as well. But you'll see carats, it's another way to represent the purity. The lower the carat number, the more of the other metals are blended into that alloy. A microscopic look, if it is homogeneous, again, very uniform throughout. You have different things there. This is just kind of a representation. If it's heterogeneous, again, as you look at the fundamental situation, it is not very uniform throughout. So again, to kind of just go back and give you a broad sense of what I just said to you, matter, you can have either a mixture or a pure substance. Mixtures can be either heterogeneous or homogeneous. The heterogeneous situation is called a suspension. If you have oil and water and you shake it up, it might look very uniform for a brief time, but it will then separate. So that would be a suspension. Homogeneous mixtures can be either solutions, things like Kool-Aid. The air you are breathing is a gaseous solution of mostly nitrogen, but you actually have some oxygen. Obviously, you and I need that. You have argon in there, carbon dioxide, water vapor, a variety of gases are in there. You have colloids, which is a thing in a liquid homogeneous thing where you have kind of a medium-sized particle. It's big enough that when you shine a light through the colloid, you can kind of see the beam, you can see the particles, but the particles are still small enough that they don't settle out on their own. If you have put a little bit of milk in a clear glass of water, it looks kind of cloudy. That would be, milk is an example of a colloid. There are particles in there. They are not so large that they will kind of come out on their own, but they are big enough that they do make the water look rather cloudy, as opposed to, say, salt. If you dissolve salt, you have sodium and chloride ions. They're very, very small. That would be a solution because the particles are so small, you can't really detect them at all. And as I mentioned, you have things like solid alloys as well. And again, let me just give you some examples of these things. Again, sand and water might be an example of a suspension. Milk, I said to you, is an example of a colloid. In fact, it turns out milk, straight from a cow, if you've ever had that experience, the cream will rise out to the top. It will come out. The process of homogenization is the process of taking that cream, which is fat, and breaking it into small enough particles that it stays uniformly distributed throughout the milk. Solutions, like I mentioned to you, you can have a liquid solution like Kool-Aid, lemonade, something along those lines, a gaseous solution like air, and a solid solution would be something like the alloys that you see. As far as pure substances, you'll notice on the right, I can either have just pure element, just one type of atom, or I can have a compound where the atoms have been put together in specific ratios, CO2, H2O. Anytime you have a chemical formula where you have different elements in that formula, that represents a compound. Here's another way of looking at this. Again, pure substance. Break it into elements or compounds as far as the pure substances are concerned. And the elements, you could have either individual atoms or molecular an atomic molecule. So like you could have O2, H2. It is just oxygen, so it's a pure element, but they have grouped together in groups of atoms, which we call molecules. And again, you could have compounds where you have either molecules or ions, but again, notice that is represented by a formula. You have specific atoms coming together in specific ratios. Now, how do you separate these things? Heterogeneous mixtures, usually you can do things like if it's, let's say it was pieces of metal in sand, you could use a magnet to separate that. Filtering is a very common thing. If you have sand and water, you might be able to do filtration of some sort. The filtrate, some terms on the page, filtrate is what goes through the filter paper. So if you had sand and water, water would be your filtrate, and the residue, the solid that would get trapped, would be your sand in that particular case. Another process, which is illustrated here, is called distillation. Distillation uses the fact that liquids may have different boiling points. As I mentioned in a previous video, when you get to the boiling point, the temperature stops rising. So if I had, for instance, alcohol and water, and you'll see that as an example here in the bottom right, what will happen is as I heat this up, alcohol boils around just around 80 degrees. It's like 78, 79, depending on what type of alcohol. But when you get up to 78 degrees, the alcohol will boil. It will rise up through this container. Notice how this is sealed. It will come over here. This is called a condensing tube or a condenser. And what's happening is we run cold water around the outside, and the vapor travels down through a tube like a straw right down the middle. As it cools down, it condenses back into its original liquid. So if I had alcohol and water, this would go up to 78 degrees. The alcohol would come across, but the water boils at 100 degrees C. That will not come across, so that will stay there. What will happen then is I can collect pure alcohol on this side. Once all the alcohol has come across, then the temperature can rise again. It will go up to 100 degrees, and then water will start coming across. So again, it's just a way to separate a mixture, like a homogeneous mixture of alcohol and water, which is a very, very common use for a still. And again, you'll kind of see that here. Again, the vapors would rise, come across, condense, and then we get our pure liquid over here on the right side. Separation of a homogeneous mixture, a couple of options here. One might be crystallization. If you had sugar dissolved in water, and this is how you'd make rock candy. The sugar, as the water evaporates, will crystallize out of the water. And again, the sugar here is homogeneously dissolved, but as that water evaporates, the sugar will crystallize out, and you'll get the sugar crystals or rock candy. If you had, say, salt water and left it in a dish, heated it or let it sit in the sun as the water evaporated, you would get salt crystals. So that's a way to separate a homogeneous mixture. Another one is chromatography. Chromatography is where you have several different dyes or pigments typically, but you can use this in different applications. There's gas chromatography and so forth as well. But the one I'm illustrating here is you have several pigments dissolved in a ink of some sort. As your water or solvent travels up a piece of paper, what will happen is some of the solvent or some of the inks are more attracted to the solvent than others. In my example here, the blue is either more attracted to the solvent in the paper, or it's lighter, or if you're doing certain kinds of chromatography, the less it weighs will help it go quicker. The heavier or less attracted thing will go slower, so that as your solvent, in this case water, travels up this piece of paper, the pigments that were in there will separate out. And that's what chromatography represents. And again, you can take this black ink and then you get a rainbow of colors, which is kind of fun to do. It's kind of a common thing. Again, just another example of the paper chromatography. And again, you will notice on the right, that's an actual example where there was some black ink, and then as the water went up this page, the pink was more attracted to everything, so it went more quickly, and the blue was less attracted and of course stayed behind and took the most amount of time to get up. If you want to separate out a compound, that's a harder thing, because now you've got to break those bonds, and that's going to require things like electricity, chemical reactions, and so forth. What I have illustrated here is electrolysis, which is the process of running electricity through something, in this case water, and what will happen then is you can literally separate the hydrogen and oxygen at these two electrodes, and you will then get hydrogen at one electrode, which you can collect, and oxygen at the other. So electrolysis would be a way of separating a compound.